Hi everyone, welcome to the SKKU 2025 Content Challenge. My name is Yupin Lin, and I'm a research scientist in quantum chemistry at IonQ. Here I want to present to you the problem I designed for the quantum challenge, which is measuring the Berry phase in quantum computing. The challenge problem consists of three parts. First, how the Berry phase appears in algebraic time evolution. Second, how we can measure it in quantum circuits. And third, how the Berry phase appear in topological phases and how we can measure it. So the Berry phase is an important concept in the algebraic time evolution, where the Hamiltonian changes very slowly in time. And if we begin with an eigenstate, the quantum state can remain at the same level of the eigenstate through the time evolution, even if the Hamiltonian is changing. So this is called the algebraic theorem. And so the quantum state will take the form. It will stay at the same level of the eigenstate, but at the same time, it will acquire a quantum phase. Yeah, so the quantum phase will include the dynamical phase related to the energy. At the same time, it will have a Berry phase, which is an additional phase. And this Berry phase is the central topic and the main character of our challenge problem. Here we will consider a simple example that is a 2x2 Hamiltonian in the form of the block sphere Hamiltonian. We can think of it as an inner product between a three-component real vector we call the block vector and a vector of the Pauli matrices. And we will consider the time evolution of the ground state under the block vector trajectory on a unique spherical shell. We will consider four different types of trajectories and compute the Berry phase along these trajectories. And we will think about what is the relation between the computed Berry phase and the form of the trajectory. So this is the first part. And in the second part, we will think about how we can measure the Berry phase with the quantum computers. So we know that if we use the all of the qubits to encode the quantum state, we cannot measure its overall phase. So you may wonder how we can measure the Berry phase. But in fact, although we cannot measure the overall phase of the quantum state, we can measure the relative phases between two different states that compose this quantum state. So yeah, so we will first think about how we can use the interference to measure the relative phase between different superposition states. Then we will use it in the measurement of the Berry phase. That is, we will use a quantum register to encode the target state under the block sphere Hamiltonian. Then we will attach to it an ancilla qubit, and we will try to encode the Berry phase to the computational basis state 1 of the ancilla qubit, and use the measurement from the interference. So this is the central topic of part 2. And after we develop the quantum circuit, we will apply it again to the four different trajectories of the block vectors in part 1 and compare the results and see if this measurement is valid. So these are the simple examples of measuring the Berry phase. And the Berry phase is actually having a broader application beyond just the 2x2 block sphere Hamiltonian. So in part 3, we will explore an important application, that is how the Berry phase appears in the topological phases and classify different phases of matter. So here we will consider a simple example, or one of the most important examples, called the Schrieffer-Heeger model, or the SSH model. So the SSH model is a one-dimensional chain of spinless fermions where the nearest neighbor Hopkins have alternate strengths. And so one important feature is that if we have a red bond being weaker than the blue bonds, and if we look at the energy spectrum, we will find that there are two different states within the energy gap. And these two states are not there when we look at the case where the red bonds are stronger than the blue bonds. An important result is that these in-gap states are H states, that is, their densities are concentrated on the edges, and we want to know how to understand that. So there is a nice feature that the H states can be related to the fermionic polarization. And the Fermionic polarization can be related to a Berry phase in the momentum space. That is, we take the momentum as the adiabatic parameter, and we compute the Berry phase when we vary the momentum within the momentum space. So questions 1 and 2 is to explore the Berry phase of the SSH model in the momentum space and see if we can get, quantized Berry phase that correspond to different phases in the SSH model. So, questions 1 and 2 are for non-interacting SSH model. In fact, we can also study the SSH model where there is interaction. So here we will introduce the nearest neighbor repulsion to the SSH model and think about how we can measure the Berry phase and compute the topological phase transitions. So here we will consider periodic boundary condition and add the complex phase to the periodic bond. Here we will take the complex phase as the adiabatic parameter, and we will compute the Berry phase and see if we can again find the topological phase transitions, but now also under the nearest neighbor repulsion. And finally, we will try to map up the whole phase diagram and try to understand what kind of phases we can have in the SSH model. Here, the Berry phase, in part 3, we will compute the Berry phase both from the 2 overlap computation in part 1 and also the quantum circuit computation in part 2. And for the quantum circuit computation, you can use any function from Qiskit or the other libraries you like. So that is it for the challenge problem I designed, and I hope you will enjoy it. And if you have any questions, please feel free to email me. Thank you very much.